Okay, hi guys. So my name is Arij, and our topic today is rational functions, reciprocal of a linear function.
Shout out Debbie. Shout out Miss Nguyen. Let's get it. Reciprocal functions is where it's at. Don't worry about your mark, I have your back. Let me refresh your memory by telling you concepts that are easy. The denominator of a rational reciprocal function cannot be zero. If you remember this, you'll be a hero. An asymptote approaches but never touches a line. If you don't remember this, you'll be behind. This is a heads up for what's about to come in the video. Listen up close so you can be your hero. A restriction is any number that makes the function undefined. Let's try to state them, but never cross a line. And behavior is the behavior of the function at the horizontal asymptote. Don't worry, there's only two ways this can possibly go. As x approaches either infinity, the function approaches the asymptote from either above or below. The behavior at an asymptote is similar, but I'll get into that during the video. By now you should have learned the gist of the rational functions goes. I hope you enjoyed this rap. Now let's get into the video stat.
So let's get right into it. So our topic is reciprocal of a linear function. So our goal is I'm able to determine key features of a reciprocal linear function and graph them accurately. Rational functions take the form fx is equal to p of x over s of x, where s of x cannot equal 0, and where p of x and s of x are both polynomial functions. Now let's think back. What is an asymptote? A line that a curve approaches but never touches, as it heads towards infinity. Restrictions. Any value for the variable in the denominator, usually x, that makes the function undefined. What is a whole? So think back. A whole is a value of x for which the function is undefined. Also a factor of a rational function that appears in both the numerator and denominator. So then these two are new things that we are going to be going to depth today. So and behavior is behavior of the function at the horizontal asymptote. Behavior at asymptote is behavior of the function at the vertical asymptote. And now a website for grade 11 review is, our great website is ixl.com. And then you can just click whatever you need clarification on, if it's in grade 11 or grade 12, like a math topic. And another website is YouTube. It's very good. I use YouTube all the time. So yeah. So then recap of previous knowledge. So simplify and graph the following function. G of x equal to x squared plus 7x plus 12 over x plus 3. So the simplified version of this is we can factor the numerator. So it would become g of x is equal to x plus 4 and x plus 3 over x plus 3. And we get this by getting two numbers that multiply to 12 and add to 7, which is 4 and 3. And yeah, so then what do we know about this function? That it has a whole. It has a whole. Sorry for my bad writing, guys. Okay, so where does the whole occur? The whole occurs as what x plus 3 is 0. So x is equal to negative 3. That's when the whole occurs. And yeah, that's that. What does the graph look like of this function? Well, it becomes linear, and I know I drew a grid out for me to show you guys on how to draw it, but I'm going to show you on Desmos because Desmos is a great website for graphing, guys. So on Desmos, I put in the equation here, and as you can see, it simplifies to linear, and if you look closely at when x is equal to negative 3, which is right here, it will be undefined. And whoop, that's undefined, guys. You see that? Yeah, it's undefined. Okay, so let's go back to that. Okay, guys, so if you were to draw it here, you make it at negative 3, x, yeah, I already wrote x, right? So over here, it would go like this, like hit the 4, and it'd be a whole at negative, when x is equal to negative 3. Okay, so that's what you know about the function, and graph it. F of x is equal to 1 over x minus 2. So the linear function related to it is f of x is equal to x minus 2, because remember, a reciprocal is just 1 over the function. So yeah, and then is there a restriction? Yes. And the restriction is in the denominator, which is x minus 2, so is equal to 0, so x is equal to 2. That's the restriction. X cannot equal 2, because 2 minus 2 is 0, and then that makes the function undefined. And then, what does the value in the denominator represent? The vertical asymptote, and basically the domain and range of the function. So, if you were to draw this out from last year, you just have a rough sketch of 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5, and I already wrote the x and y, so yeah. And then, so you know there would be a vertical asymptote when x is equal to 2, so x cannot equal 2, so we are going to just draw the vertical asymptote and make it x equal to 2. And then the y-intercept is found by when x is 0, so it's going to be 1 over 0 minus 2, which is going to equal to be 1 minus 2. So that is right here. And roughly, we would ask you to sketch it. It would go like this. I completely missed that. And yeah. So new stuff, yay. Okay, so a basic reciprocal function takes the form f of x is equal to 1 over x. The linear function related to this is f of x equals to x, because remember, reciprocal just 1 over the function. Yep. So now, state the domain and range of the function. So the domain is figured out by, you figure out the domain by the denominator of the rational function, and you figure out the range by the numerator. So let's do vertical asymptote and horizontal asymptote first, so you understand it. So the vertical asymptote, like I said, is determined when the denominator is equal to 0, because that makes it undefined. So it's going to be when x is equal to, so basically in this, x is equal to 0. X cannot be 0. Or no, that's a big mistake, a classical mistake, as Ms. Newman would say, that people make, is when we're writing the vertical asymptote equation, it's x equals to 0, but when we're writing the restriction, like for the domain, we're going to do x belongs to all real numbers, x cannot be 0. So guys, that's a mistake that many of you, like me, just made. So yeah, that's a vertical asymptote. Now the horizontal asymptote is when the numerator is 0, so it's going to be 1 is equal to 0, and that cannot happen. So when it is a constant, we just say that the horizontal asymptote is 0, so y is equal to 0. So then the range is going to be y can belong to any number, any real number, such that y cannot be 0. Wow. And if you see, these are, the zeros are asymptotes, x and y. Okay, so now state the end behaviors of the function. So end behavior is as x goes to negative infinity right here, y goes to the vertical asymptote, no, the horizontal asymptote from below, or goes to 0 from below, and then as it approaches positive infinity, it goes above. So yep, above the asymptote. So behavior at the asymptote. So when x goes to 0 from either above or below, so if it goes from above, it's going to be right here, and it's going to go to positive infinity. And if it goes from below, it's going to be negative infinity. Okay, so now transformations of a linear reciprocal function. So in the form f of x is equal to a over k x plus c, when a or k is positive, the graph looks like. Okay guys, so as I was saying, when f of x is equal to a over kx plus c, when ak is positive, the function is positive, the graph will look like the blue one. So you can see that the blue one has, the right branch of it has a negative increasing slope, and the left branch has a negative decreasing slope. And you can get the slope by doing a tangent line and getting 2 points on it, yep. And then, and I'll show you when ak is negative, the graph looks like this. No, when a of k is negative, so either a or k is negative, because if you have both negative, it will be positive. So when that is negative, you're gonna get the red graph, and the red graph basically, the left branch has a positive increasing slope, and the right branch has a positive decreasing slope, because as you can see, it's still positive, increasing, yeah. So yeah, that's that, guys. In conclusion, when the function is positive, or a or k is positive, the right branch of the reciprocal function has a negative increasing slope, and the left branch has a negative decreasing slope. And when ak is negative, like either a or k, like I said, the left branch has a positive increasing slope, and the right branch has a positive decreasing slope. And I showed you this in decimals, on decimals. So yeah. So now, example 1, yay. So f of x is equal to 1 over 2x minus 1. So the linear function related to this is f of x is equal to 2x minus 1. Yep. And now the vertical asymptote, like I said, is when the denominator is equal to 0. So it's going to be 2x minus 1. So that's going to be 2x is equal to 1. X is equal to 1 over 2. Wow, that's our vertical asymptote. And remember, it's an equal sign, because it's not an intersection. And now the horizontal asymptote is when the numerator is a 0. And you know when it's a constant, it's going to automatically be 0. So that's that. And the domain and range, domain we look at the denominator, and range you look at the numerator. So vertical asymptote and then horizontal asymptote. So it's going to be x belongs to all real numbers such that x is greater than 1 over 2. No, x cannot equal, sorry, 1 over 2. So then the range is y belongs to all real numbers such that y cannot equal to 0, because those are the two asymptotes. End behavior, what is the end behavior of the function? I remember end behavior is the behavior of the function at the horizontal asymptote. So we're just going to plug these 2 points in. So f of x is equal to 1 over 2, negative 100, minus 1. That will give you a negative number. And because 1 over a negative number will give you a negative number. And 1 over, it will give you a negative number close to 0. So then the positive is, we just plug in a positive, and it will give you 1 over 200 minus 1, which is equal to 1 over 199, which is a positive. So the end behavior, as x goes towards negative infinity, y goes from 0 from below. And as x goes towards positive infinity, it goes to 0 from the asymptote from above. So now, what is the behavior at the asymptote? So let's just get points. So the asymptote, behavior of the asymptote means the vertical asymptote, behavior of the function at the vertical asymptote. So the vertical asymptote from this function is 1 over 2, like we stated up there. So then we're going to get points that are smaller than 1.2 and points that are bigger than 1.2, because remember, no, 1 over 2. Because remember that we can't have that. We can't have 1 over 2 because that's an asymptote. So then when you do this on your calculator, you will get negative, you just plug it in like we did over there. You will get negative 2.5, negative 5, negative 10, negative 16, and 0.6 altogether, so it'll be 2.5. And another one will be 1.67. So as over here, we can see that the behavior at the asymptote will be as x goes towards 0 from either above or below. The asymptote from above or below. It should be 1 over 2, but you know it's okay. Y goes towards what? So as it goes towards y from like more than 1 over 2, more than 0.5, it will be positive, towards positive infinity. So if it goes below, less than the vertical asymptote, it'll be a negative. So state the x-intercepts and y-intercepts. So remember before I told you that to get the y-intercept, you would have to make x equal to 0. Ha, yeah. I don't know why I wrote brackets, it doesn't make sense. So when x is equal to 0, so f of 0 is equal to 1 over 2, 0 minus 1. So your y-intercept, sorry, will be 1 over, will be negative 1 over negative 1, which is going to be negative 1. And then for your x-intercept, you don't have any because your x-intercept is when your y is equal to 0, and then you can't have this because if you multiply here, you're going to get 0 is equal to 1, and you can't have that, so you have no x-intercepts. X-int, sorry, oh my god, my writing is terrible. None. So now it says sketch a graph. So let me just label the graph out first. 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. Okay, so now we know that the vertical asymptote is at, no, the horizontal asymptote is at 0. So we're just going to write y is equal to 0 and do that. And then we know the the vertical asymptote is at 1 over 2, which is 0.5, which is going to be right here. And that's going to be x is equal to 1 over 2. So then that's that. And then we know that the end behavior as a function goes from below. So this is towards the vertical asymptote. So we're going to look at behavior at the asymptote. As it goes below half, it's going to be negative. So it's going to go down this way. And then as it goes from above the, where is it? above the, like more than the asymptote, it's going to be, like on the right side, it's going to be positive. So it's going to be up here. And then our y-intercept, we should do y-intercept first. Sorry about that, guys. So our y-intercept, remember, it was negative 1. So our negative 1 is going to be right here. That's our y-intercept right there. And we kind of already know that it's going to go like this. But let me just clarify the behavior, the end behavior of the function. So remember when it goes to negative infinity, it's y from below, so it's going to be right there. We can clarify. Okay guys, so sorry for the cheating background and technical difficulties. This is the setup. Yeah, sorry about that again. So yeah, so basically let me just focus it. Great. So as we were saying, at the behavior at the vertical asymptote is behavior at the asymptote, and as x is above the asymptote, like more than the asymptote, it's going to be plus, so it's going to go towards positive infinity, so that is right. And then as the end behavior of the function as x goes towards positive infinity is above the 0, right there. So it's going to be like this, and that is your graph. Good job. And then after, so to describe the intervals of where the slope is increasing and the intervals where the slope is decreasing. So remember when I said in conclusion when AK is positive, the right branch of the reciprocal function has a negative increasing slope and the left branch has a negative decreasing slope. So the when slope is increasing, I'm going to try to avoid my answer. So it's increasing on the right branch. So it's going to be 1 over 2 to positive infinity. It's from 1 over 2 to positive infinity. And then it's decreasing when it's negative infinity towards 1 over 2. Okay guys, so it says how to determine the equation from a word description. Determine the equation of a linear reciprocal function with a vertical asymptote at -6 and a y-intercept at 1 over 3. So let's start with the vertical asymptote. So we know the vertical asymptote is always in the bottom of like the denominator. So it's going to be x minus 3, so you know it's going to be x plus, no, minus 6. It's going to be x plus 6, because if we do x plus 6 is equal to 0, it's equal to x equals negative 6, and that's right. So that's your vertical asymptote, that's right. But then they say there's a y-intercept at 1 over 3. Now to make, y-intercept is when thing is 0. So if this was it would be 1 over 6, and that's not the y-intercept we want. So if you add, you have to think of something that can make this equal to 1 over 3. So a factor of 6 is 2, so you can make it, the numerator is 2x plus 3. And it still has, and that's great because, no, sorry. It's going to be 2 over, it's going to be f of x is equal to 2 over x plus 6. And then if you simplify 2 over 6, it's going to be 1 over 3. And that is right. So that is your final answer. And then now from a graph, so this is a graph and it's kind of blurry, but we can see that this is 1, this is 0.5. So the vertical asymptote is at 0.5, and you know we can't write that in the denominator, or else most students will take marks off. So it's going to be 1 over 2 x, right, is equal to 0. So then we're going to do, 1 over 2x. So it's going to be f of x is equal to 1 over, and 0.5, right? So that's 2x minus 1, because if you do 2x minus 1 equals to 0, it's going to be x is going to equal to 1 over 2 if you simplify that. So then that's your equation, because the horizontal asymptote is y is equal to 0. So that's that. So then the word problems. So word problems. The Newens family is traveling to a lake. The oldest child, Kim, determines that the distance from their home is 130 kilometers. So how long will the trip take if Miss Newton averages 60 kilometers per hour, 80 kilometers per hour, and 110 kilometers per hour? So basically, the distance is 130 kilometers, and the speed is 60 kilometers per hour. Now, if we want to get hour, like if I put it this way, you can tell that if I divide these two, you'll get hour, because the kilometers and kilometers cancel out. So the time equals distance divided by speed. Wow. And that's going to be speed. So it's going to be 130 kilometers divided by 60 kilometers per hour, which is going to give you, so it says, write a function that describes the time it takes to make this trip as a function of the speed of the vehicle, and identify the meaning of the variables. And you can see up here, we kind of already did it, so it's going to be, but it says as a function, write a function as a function of the speed. So it's going to be t, the time it takes as a function of speed. It's going to equal distance over speed. So distance, speed, time, speed, time depending on speed. So now over here, speed will be our thing, and you know that time can be negative, so this part is just blocked out. And then if we just plot these on our graphs, we will get, actually let me just erase these and write the actual thing. So an hour can be 1, 2, 3, 4. Function of part B, we're just going to add random speeds into the equation. So 130 over a speed is going to be how many hours it's going to take. I don't know why I wrote points. So then I already wrote a table of constants, whatever. I wrote a table, so then I just plotted these points in, and it says, what does this graph tell you about the time it will take to travel depending on the speed of the car? So as you can see, as the speed increases, time decreases. So as speed increases, time decreases. And we are done.